Hi everyone, this is the video instruction for CPE100L laboratory number 7, which is 2-bit ALU and 7-segment display. So first, let's start with what is ALU. So ALU, arithmetic logic unit, which is the electronic device that is able to perform some predefined set of logical and arithmetic operations. So if you look at ALU as a black box, then you will have two operands, so two inputs, and we need to select one of operation. So we also have to have operation selector, and then of course we have result of the operation, which will be our output. So let's look at some examples. So two operands, 2 and 3, so decimal numbers, and operation will be arithmetic sum, and our result will be 5 in this case. 1-bit ALU, what does it mean? It means that each of the operands, they are 1-bit numbers, binary numbers. And of course, again, we have operation selector. So let's choose AND, and our result will be 1 and 0 will be 0, because this is logical operation. For 1-bit ALU, even if these are 1-bit binary numbers, of course we also can have arithmetic operation. So let's have sum, and 1 plus 1 is 0, carry out 1. Like you remember full adder. Arithmetic operation. Okay, so if you look at this kind of structure, that we have some set of operations that we can choose from, and we have fixed number of inputs and one output. What does it remind you? It should remind you the multiplexer, correct? So we have multiplexer. We have it here for our 1-bit ALU that we will be working with in this class. So in our 1-bit ALU, we'll have logical AND or XOR and arithmetic add. So for our multiplexer, we have operation selectors, so we can label. So 0, 0, 0, 1 for OR, 1, 0 for XOR, and 1, 1 for add. So what are we choosing? What are inputs to the multiplexer? So they are results of each of these operations. So when we choose, for example, 0, 0, so this will be AND. So then this input becomes active, right? And it gets logically connected to the output. These outputs are inactive at that point, but remember that correct results of OR, XOR, and ADD are just waiting here. They are here because selectors, they impact the multiplexer inside, but they don't impact what happens here. And you can see that when AND is selected, 0, 0, then what happens, for example, with OR gate? You can see that the values from A and B, they still go here. They are still connected. Nothing changes here. So it means that XOR is here. The value of OR is here, right? Because A and B are provided same values as for and XOR and full adder. For the full adder, you have to remember that some output is connected to a multiplexer and Cout is not. So value of Cout doesn't go through multiplexer. So how we approach that, not to complicate our 1-bit ALU, is that we just don't look at Cout when AND or XOR are selected. We consider Cout as a valid value only when selectors, they have values 1, 1, and they are activating add input to the multiplexer. Okay, so this is 1-bit ALU. We will also work with 2-bit ALU. 2-bit ALU means that it takes 2 operands, and each of these operands is 2-bit. So our notation will be as follows. So A0 will be first bit of the first argument, A1 will be second bit of the first argument, same by analogy with B, and Y0 will be first bit of the output, and Y1 will be second bit of the output. So take a look at the example here. If we draw the black box, we'll have A0, A1, B0, B1, selectors, S0, S1, or S1, S0, right? And Y0, Y1. So how do we do bitwise operation? Because we will be this means bitwise. So take a look at the AND example. Here we can see position of the bit. So this is position 0, this is position 1, and my number A, my operand, my argument A, we are talking about arguments, okay? So my argument A is A1, A0 number. My argument B is B1, B0 number. So looking at the values, these are some example values. So my A number is 1, 0, and this is position 0, this is position 1. So how we do the operations? We are doing AND, logical AND. So we are ANDing these two values, and the result will be Y0, which is this one. Then in order to get the value of Y1, then we have to AND these two values, and then we'll receive Y1. So this is bitwise. This is bitwise operation because we always perform the operation on the bits on the same position of two arguments, like you could see here. So this means that for bitwise AND, my Y0 will be A0 and B0, right? So you can see that these bit positions are same for the entire operation. So this is bitwise, right? Bitwise. Because we operate on bits, same. Right? Okay. For the arithmetic add, here you can see how this is calculated. But you should also remember that from the previous lab, because we were doing this. Okay, next thing, 7-segment display. So second part of our lab. Everyone knows 7-segment displays. We have them, microwaves, stoves, they are like literally everywhere. So 7-segment, why 7-segment? Because they represent digits, and each display has 7 segments. If you look here, so at more technical side, here are the segments, and we start with the top segment, which we denote as A. Then we have B, C, D, E, F, G, so 7 segments. And this is how the part looks like that would be used on the breadboard. Electronically, looking at that, so we have LEDs. So this is the schematic. And what can we observe in here for this schematic? You can see that anodes of these segments are all connected to the same point, right? Because you remember that LED has anode and cathode. So if anodes are connected, then it means that in order to change the value of each of the segments, then we manipulate cathode values. And as you remember from the previous labs, how we connect LEDs is that in order to get the current flowing through the LED, so in order to light it up, then we have to connect the cathode to the ground, so 0 volts. Right? So it means that this has to be VCC all the time, because the VCC will be provided to each of the inputs of these LEDs. So we have to keep VCC here, and we are changing cathode values in order to manipulate their state. Either they will be lighting up or they will be turned off. So this also means that if we have logical 1 here, then in order to light up this LED, then we have to provide 0 here. Then current flows through LED and the LED is on. If you provide logical 1 here, then there is no current flow because there are the same voltages. So this means that in this arrangement, in order to activate the LED to light it up, then you provide a value of 0. Because this is called common anode. There is of course also common cathode, but in this lab we work with this arrangement. Okay, so now you know what is inside of 7-segment. So these are LEDs that you are familiar with already. But the question appears, so if 7-segment has 7 signals, right? Because we have 7 segments in here, and our number, single digit, has 4 bits, so BCD number is 4 bits, 4 signals. So how to convert? How to go from, for example, 101 on the BCC side into this kind of form, right? How to convert this? So in order to do that, we are doing the decoders. So 7447 is the example of the chip that can convert BCD number to 7 segment. And it has a lot of like control inputs. We are not looking at that. What are we interested in is that you can see it has 4 BCD inputs and 7 outputs. And these 7 outputs, as you can see, they are connected to A, B, C, D, E, F, G, that are inputs to our 7-segment display. So this chip will do the conversion for us. You can see the resistor here in Quartus and also in our DE0 board. You don't have to worry about the resistor in here. But in case of wiring on the breadboard, then you would have to either place the resistor here, or better approach is to have 7 resistors for each line for some specific reasons. Okay, so this is everything about 7-segment. Now for the pre-lab. Part number 1 of the pre-lab is to apply the rules of K-map to find the expression for each of 7 outputs, right? So in fact, here you have the 7447 table, and you can see that the combination for each number, how it's represented here, how it's represented in the 7-segment notation. So you have to write K-maps for each of these outputs. Part number 2 is to take 1-bit ALU that you have in the lab instruction and implement that in Quartus. You already have the multiplexer, or you can use the predefined multiplexer that is in Quartus, and then do the simulation. Part number 3 is to do 2-bit ALU. So here is where you have to excuse me, design 2-bit ALU. And you have to do this for the pre-lab because there will be one experiment for that. Okay, so how to approach this problem? I will show you just the beginning, and then everything should be clear for everyone. Okay, so this is our 1-bit ALU. So we have A and B, and you remember that for 2-bit ALU we have A0, A1, B0, B1. So how to approach this problem? Okay, so let's start with multiplexer. So this will be Y0, and I will have AND gate. Let's start with AND gate. And like we said, what kind of input do we have? So we have A0, A1, and for B, let me have some different color. B0, B0, B1. And you, from the slide, you remember that Y0 is A0 and B0. Okay, so Y0, so this will be A0, A0, and B0. Okay, so we have Y0. Now Y1. So how to approach? Of course, we have to have second multiplexer. So let's have second multiplexer. will also have two selectors, and this multiplexer will be responsible for while 1. And again, let me have my AND gate. And let's look at the slide. Y1 equals A1 and B1. Okay, so A1 is here, B1 is here. I guess looks good, right? So now I have implemented Y0 and Y1. So let's have that this will be 0, 0, like in previous examples. So how do we control these multiplexers? So of course, if we want to choose operation AND, which is 0, 0 in selectors, then we want to have the same operation AND on both multiplexers. And same for any other operation. We don't want to have different operation on this multiplexer and different and some other operation on this multiplexer, right? We don't want that. So so we have to connect selectors together because they will have exactly the same values respectively. So I'm connecting S1 to S1, S1, S0, S0. So this is S1, S0, S1, S0 of the second multiplexer. And now we're good because if I select 0, 0 here, then same values I will have here. So same operation will be selected on both multiplexers. If I select 0, 1 here, then automatically I have 0, 1 here, and then operation 0, 1 is selected. That will be OR. Okay, so this is actually first step of your pre-lab. So start with that. You have operation AND already implemented for your 2-bit ALU. So you need to add OR, XOR, and arithmetic add. So these two logical functions, OR and XOR, they should be like really easy because this will be same thing as for this arrangement. With full adder, then you will have to, of course, connect C-in and C-out, but you did that already in full adder lab. So I hope there will be no problems with this. So this is all about the pre-lab. Now about experiments. Experiment number 1 will be just to test how the decoder works. So we will be providing 3-bit BCD number, and then you will be transforming that into 7-segment. And you noticed already that you have multiple 7 segments on your board. So then you choose one of them and use it. So you use the decoder in this case. So actually there should be one question even before. Here we have 3-bit input. So the maximum number will be 7. But here you can see 4 bits. So of course we can, using 4 bits, we can provide not in this case, because in the class we want to use just the 3 bits, but here in this arrangement, in this circuit, we can have 4 bits. So we can provide 8, 9, but we can provide up to 15. So for numbers that are 10 or higher, then some symbols will be displayed here. Some symbols, just to let you know. But in our lab, we are using only 3-bit BCD numbers, so the range will be from 0 to 7, so we don't have to worry about going over the range. Experiment number 2 will be implementing 1-bit ALU on the B0 board. So actually you already will have the schematic, because you do this for the pre-lab. Experiment number 3, implementing your design of 2-bit ALU on the E0 board. Experiment number 4 is to take experiment number 3, and instead of demonstrating the arithmetic result of your addition, instead of representing that as LED signals, as binary signals, then you represent that as 7-segment number. So you will just add 7-segment and the decoder to your ALU and make it work. Okay, so this is everything about explanations I wanted to give to you. I hope that this will really help, and you will have no problems with the pre-lab and also no problem with experiments. Thank you so much for watching.